Welcome to the organic chemistry section of our practice MCAT questions. In this video, we're going to be going through questions 106 to 110. So first, I'll show you guys the questions so that you can pause the video and attempt them on your own. Here's question 106, 107, 108, 109, and 110. Now let's go through the questions together. In question 106, it says the amino acid tyrosine has a pKa between 10 and 10.3, so 10.0 and 10.3. If a given solution of tyrosine is brought from pH 9 to pH 11, what do you expect to occur to its side chain? So we're talking about tyrosine. Its pKa is between these ranges. Now we have a solution that was initially at pH 9. Now it's at pH 11. What would occur to its side chain? So what do we expect? Well, the side chain for tyrosine, you should know it has a phenyl group, which means that there's an OH group at the end. So really it's that OH group that's protonated or deprotonated. And its pH, its pKa is, let's just say 10.15 or 10.2, around 10.2. So in that range, it's close enough to 10 as well. So it's like 10. What does that tell us about, what does the pKa tell us about whether that side chain is protonated or deprotonated? So you should know based on the Henderson-Hasselbalch equation that a pKa is telling us the pH at which, if we have an acid, it's 50% protonated, 50% deprotonated. So the concentrations of those are 50% each, so a 1-to-1 ratio. So at the pKa, if we have this pH, we have a solution of tyrosine that's half protonated, half deprotonated. If we go below this, about 1 pH value, then we have, since we're more acidic and we have more protons present, we're fully protonated, so 100% or almost 100% of the protonated form, and vice versa. If we go above 1 pH value, then we're fully deprotonated. And so we had something that was at pH 9, that's approximately 1 below the pKa, so it was fully protonated before, and then we brought it to 10, and then we went beyond 10 and went to 11. Now it's fully deprotonated. So option A is saying the hydroxyl will go from being fully protonated at pH 9 to deprotonated at 11. And this is correct on both accounts, so therefore it's the correct answer. Whereas option B is saying it'll go from being deprotonated at pH 9 to being protonated at pH 11. That doesn't make sense because that's backwards. When we have a lower pH, we have a more acidic environment, so it's going to be protonated at that environment. Option C is saying the hydroxyl will remain deprotonated during the pH shift. No, if you understand what pK means and then what these pH shifts are telling us, then you know that there's a change. And likewise, D is incorrect. It's not completely protonated the entire time. In question 107, it says acetone and acetyl chloride are shown. Regarding deprotonation of a hydrogen from the left methyl group, which molecule will have the lower pKa and why? We have acetone and we have acetyl chloride. And you should be able to interpret names and match them with structures for organic chemistry. So acetone is here, acetyl chloride is this one on the right. Now we're talking about deprotonation, and we're talking about a hydrogen from the left methyl group. So one of these hydrogens, that's what we're deprotonating. That's what we're talking about when we're talking about acidity here. Which molecule will have the lower pKa and also why? So lower pKa means that something is more acidic. So which one is going to be more acidic? In general, this carbon-hydrogen bond is not that acidic, but because we have resonance happening, because we're talking about a carbon that's alpha to a carbonyl, it's more acidic now. Which one relatively is a more acidic one? Well, when we have this deprotonated, what essentially happens is this will become a 2, and we have a negative charge here that resonates, and it can be picked up by the oxygen. So we have a negative charge, carbon doesn't want to hold that negative charge for too long, so resonance occurs. The main difference is on the right side, For the acetone, we have a methyl group, whereas for the acetyl chloride, we have a chloride, which you should know is electronegative, therefore it has electron withdrawing effects. So if we think about that, the chloride has electron withdrawing effects, which means that it can more so stabilize the conjugate base that's formed because it can pull that electron density towards itself. Therefore, the one on the right is a more stable conjugate base. If your conjugate base is more stable, it's more likely to be formed. The acid is more likely to be deprotonated. So the one on the right we can say is the more acidic one, the one with the lower pKa, once again, because of the inductive effect of that chloride. Option A is saying acetone will have the lower pKa and it'll destabilize the conjugate base. That doesn't make sense. If you have destabilization of the conjugate base, why would you have a lower pKa? And also acetone is not the right one. Similarly, B is also removed. C is saying acetyl chloride will have the lower pKa and it will stabilize the conjugate base. That's true. D is incorrect because it's saying it will destabilize the conjugate base. If you destabilize it, then you wouldn't have the lower pKa. So if you understand what we're talking about when we're talking about high versus low pKa, you should know that D is an incorrect answer and C is the complete answer. In question 108, we're asked which of the following modifications would increase the acidity of the hydroxyl group in the compound shown. We have some modifications going on. We want to increase the acidity. We're talking about the hydroxyl group here. So we want to increase acidity, meaning we want to make it more likely to be deprotonated. So if this acts as an acid, the hydrogen goes away, we have a negative charge. Always think about what's happening. Like if we're talking about an acid, then we're having a negative charge being formed. Think about what happens when we have a base. So always think about it in terms like that. So the acid is losing the hydrogen and then therefore getting a negative charge. Something that would make this more acidic is if somehow the conjugate base was stabilized more. And so that would happen if there's something which can take up the electron density as well. Option A is saying addition of methyl groups to the benzene ring, and that would be incorrect because if you added any methyl groups here, that would make the molecule more electron donating. Methyl groups are an electron donating group, so they donate more electron density into the system, and now we have even more electron density. You want something which can take up electron density itself, not add more to an already negative system. That's going to destabilize the conjugate base. So it does the opposite. It will decrease the acidity. Option B is saying replacement of the hydrogen atoms in CH2OH with two methyl groups. So if instead of hydrogens here, we just had this methyl group, same thing, it would have more electron density and therefore more like electron donating effect, and that's the opposite effect of what we want. Option C is saying adding HCl to the aqueous solution of the compound. No, you should definitely know to remove this answer because if you add HCl, sure, you made the overall solution a more acidic solution, but you didn't change any real property of the molecule itself. You have to make a covalent modification to the molecule rather than just changing the environment that it's in. Because if I took away this HCl, it doesn't mean that the molecule itself has changed and become acidic if I put it in some other solvent. So it's not the solution that it's in or the environment that changes as much the acidity of the compound. We're talking about an actual fundamental property of the compound itself. So D, the remaining answer, is the correct answer. If we added chlorine atoms to the benzene ring, for example, if we added one here, you can add it anywhere. The point is, this is something which has electron density that it can take away. If we're talking about the inductive effect, it's an electron withdrawing molecule. When you learn about like aromatic systems and attack that the benzene is attacking, then chloride, yes, you would learn as an electron donating group, but try not to get confused with that. Right now, think about the chloride as it's helping in the conjugate base system, and what it can do is because of its high electronegativity is pull that electron density towards itself, so it has somewhere to go in the molecule. Instead of just staying by that oxygen, it has somewhere else to go. Because of that, the conjugate base is more stable, and this increases the acidity of the hydroxyl group. So this is the correct answer. In question 109, it says, based on its name, the enzyme RDB phosphorylase kinase would be expected to blank. So we are talking about this enzyme, And note, for a lot of enzymes, their name kind of puts them into a class and gives away what their function is. So in this case, we are talking about a kinase. So if you know what a kinase does, then this question should be easy. So what a kinase does is it adds a phosphate group to something. And in this case, it's called RDB phosphorylase kinase. So therefore, you should know that to RDB phosphorylase, this molecule is mentioned, a kinase will add a phosphate group. So our correct answer is C because it adds a phosphate group. There's a different class which removes a phosphate group. A is saying be a transmembrane protein. There's nothing in the name that makes it clear that's a transmembrane protein, and a kinase makes it pretty clear that it's something that adds a phosphate group. It's possible that you can have something inside that's hooked up to a membrane that could be a kinase, but this is specifically talking about a transmembrane protein, so it's talking about something that most likely is going to act as a channel between the outside and the inside, or between two different cells. And so there's nothing clear in the name that we can have an expectation or draw an assumption saying that this is the function of the enzyme. And D is wrong as well. Decarboxylation happens with another class of enzyme, decarboxylase, and so it's not what a kinase does. In question 110, we're asked which of the following reactions produces a double bond from two sp3 hybridized carbon atoms as shown in the diagram below. So we want a reaction which produces a double bond. An SN1, you should know, would not. In an SN1, what happens is the leaving group leaves, and then what we end up getting is a carbocation, which will look like this. Hydrogen here, and then some nucleophile is going to come and then attack that carbocation, and what we get is again two sp3 hybridized atoms. Similarly, an SN2 also leads to two sp3 hybridized atoms because we get attack by some, so this is SN2 now. We get attack by some nucleophile over here, leaving group leaves. So that would be SN2. That happens at the same time. So in both the SN1 and SN2, we have a substitution that's going on. That's why they're called, substitution reactions. And then 1 and 2 talks about how many, if we have a bimolecular or a unimolecular reaction. So in the rate determining step, how many molecules are involved. But either way, they still lead to two sp3 hybridized atoms, meaning single bonds, not double bonds, and they have a substitution. We're talking about something with a double bond, which means that we have one thing going away. So what that would look like is essentially like this. If we had hydrogen over here, hydrogen, R, and then R. You can notice that we don't have a substitution. One thing wasn't replaced by another, but rather we have something going away and not coming back. Therefore, it was an elimination. And E1 is correct. It's an elimination type reaction, not a substitution reaction. And in an E1, we have a similar thing over here, where initially the leaving group is going to leave, and then we have the carbocation, and then in SN1, what would happen is the nucleophile would come and attack, versus in E1, what happens is some base comes, takes this hydrogen, we have a double bond over here, and therefore we have no more charges. We get this double bond structure over here, so only an elimination type reaction would do that. So A is correct, it's number 3 only. That's it for the questions in this video. If you enjoyed what you saw, make sure to check out our course. The link is in the description as well as right here on the page. And in that course, we go through a lot more questions just like this video and explain all the different answer options. Other than that, make sure to subscribe here to this channel to stay up to date with the videos that we post here. And that's it for this one.